Have you ever wondered what math is all about? I know the thought probably hasn't crossed your mind today, but every day is a chance to learn something new. Maybe today is the day you'll understand that mathematics isn't just about numbers and formulas. Maybe today you'll see the vast space that math occupies in our daily lives. Maybe today is the day you'll see things differently. Hi, I am Loren.
Hi, I'm Elizabeth.
Hi, I'm Adrian.
Hi, I'm Phoebe.
And this is What About Math? Before we start with today's video, I just want to take this opportunity to say that I hope you're all doing well during this time of pandemic. I know that it is not easy to adapt to this sudden change in our lives, but let us continue to pray, have faith, and trust in God's plan. With that being said, let's go on with the video.
What is mathematics? When we hear the word mathematics, the first thing that we think about is numbers. And although numbers are the heart of mathematics, they are only a piece of the whole definition of mathematics.
To really understand what math is about, you first need to look around your surroundings. You see the simplicity of the world as you know it. But the truth is, we live in an intensely mathematical world. However, you don't see it or even think about it. It's because we're used to knowing that the world is just how it is.
The thing is, we can't deny the fact that math cannot be hidden from the world. You may not be aware, but we use math every day. In fact, we use it to count the eggs that we buy from the groceries. We use it to subtract the change from the money that we paid for it. And without the ability or awareness for math, we simply can't even buy our own food.
Just like reading and writing that's been taught to us for years, math is an essential part of living. The numerical components that we learn are just cutting above the surface of what math is really about. To know math, one must first know the basics. It's pretty simple, really. Just start counting.
Math began with numbers and numbers began with counting. Counting began way before there were numerical versions of it such as 1, 2, and 3. Because back then, you can easily count with your fingers to know how many camels you sold or have by folding down fingers as your eye glances over the camels. You can also record a count as scratches on pieces of wood or bone.
Years later, people began to discover the use of symbols.
After the development of symbols comes the fractions. It's kind of number that we symbolize as 2/3 or 22/7, or equivalently 3 and 1/7.
Much later, between 400 and 1200 AD, the concept of zero was invented and accepted as denoting a number. Many history books say that the key idea here was the invention of a symbol for nothing. That may have been the key to making arithmetic practical. But for mathematics, the important idea was the concept of a new kind of number, one that represented the concrete idea, nothing.
The next extension of number concept was the invention of negative numbers.
Fractions are all you need for most commercial transactions, but they're not enough for mathematics. For example, as the ancient Greeks discovered to their chagrin that the square root of 2 is not exactly representable as a fraction. You can get very close. For example, the square of 17 over 12 is 289 over 144. And if only it were 288 over 144, you would get 2. But it isn't. And whatever fraction you try, you never will. Just like having a crush. You insist that you might end up being together, but in reality, no matter how hard you try, you never will.
You never will.
As we were saying, the square root of 2, usually denoted in this type of symbol, is therefore to be said irrational. The simplest way to enlarge the number system to include the irrationals is to use the so-called real numbers, a breathtakingly ironic name. That is, if you consider decimals that go on forever as real numbers. Imagine 3.14159 where the dots indicate an infinite number of digits. How can things be real if you can't even write them down fully? But the name stuck, probably because real numbers formalize many of our natural visual intuitions about lengths and distances.
In current terminology, the whole number of 0, 1, 2, 3, and so on are known as natural numbers. If negative whole numbers are included, we have the integers. Positive and negative fractions are called rational numbers. Real numbers are more general. Complex numbers are more general still. So, here we have 5 systems, each more inclusive than the previous. Natural numbers, integers, rationals, real numbers, and complex numbers.
However, mathematics is not just about numbers.
We've already had a passing encounter with a different kind of object of mathematical thought, an operation. Examples are addition, subtraction, multiplication, and division. The third type of mathematical object, of course, is the square root. If you start with a number and form its square root, you get another number. The term of such an object is function.
Functions are often defined using algebraic formulas, which are just shortened ways to explain what the rule is, but they can be defined in any convenient method.
Operations and functions are very similar concepts. The image of mathematics raised by this description of its basic object is something like a tree, rooted in numbers and branching into more complex data structures as you proceed from trunk to bow, bow to limb, limb to twig. But this image doesn't have the essential ingredient to describe how mathematical concepts interact.
Mathematics is not a collection of isolated facts. For instance, there is the metaphorical feeling of distance. Near any particular mathematical fact, we find other related facts.
At every turn, something new and unexpected arises. The user of mathematics only ventures to the already familiar territory that they understand. Meanwhile, the creator of mathematics explores the mysteries and builds something from the discovery so that it can be accessible for everybody else. The ingredient that knits this landscape together is proof. Proof determines the route from one fact to another.
Proofs must be convincing to be accepted by mathematicians. There have been many cases where extensive numerical evidence suggested a completely wrong answer.
Even the very best mathematicians have an occasion to claim that they have proved something that later on turned out not to be. So, their proof have a subtle gap, or there was a simple error in calculation, or they inadvertently assumed something that was not a rock solid as they had imagined. So, over the centuries, mathematicians have learned to be extremely critical of proofs. Proofs knit the fabric of mathematics together, and if a single thread is weak, the entire fabric may unravel.
And on that note, that is the end of our seemingly long introduction to the world of mathematics. We hope that you guys were able to appreciate more the great efforts that our mathematicians put into creating a more sensible way for us to comprehend the complexities of mathematics in our lives.
We also hope that you give this a like if you enjoyed our video. Make sure to leave us a comment on what you want us to explain next on this math segment we made. And make sure to subscribe so that you can watch more content like this one. Bye!